Okay, let's prove theorem 12.2. So the hypothesis is that we have a sequence of real numbers, Sn, and each term is non-zero. And our goal is to prove this string of inequalities. So what I'm going to do is I'm going to call this first inequality that liminf of this, the absolute value of this ratio, is less than or equal to liminf of the nth root of the absolute value of the nth term. So I'm going to call that number 1. And then we can call this inequality here number 2. And then the third inequality will be number 3. Okay, so this statement, the statement of the theorem, is that these 3 inequalities always hold. So the proof of the first and the third are similar. I'll do the third, and then the first I think is like a homework assignment, and then I'll talk through the proof of the second. We'll do the second inequality first because it's actually the most straightforward. When we compare liminf and limsup of the same sequence, of course, liminf will be less than or equal to limsup, and that's just going to be because for each n, right, the infimum of this set, the tail end of our sequence, is going to be less than or equal to the supremum, right? So, we'll have 2 sequences, and each term in this sequence is going to dominate each term in that sequence. So the limit of this sequence is going to be bigger than or equal to the limit of that sequence. And now let's look at step 2, which is to show, we're going to show this third one here. So our goal is to show that limsup of the nth root of the absolute value of Sn is always less than or equal to limsup of the absolute value of the ratio of the consecutive terms. So just let alpha be our first quantity and capital L be the second quantity. What we want to show is that alpha is less than or equal to L. And as usual, we have 2 cases, and our 2 cases are going to be based on whether or not L is finite or infinite. So if L is plus infinity, then let's see here. Well, if L is plus infinity, well then by convention, whatever alpha is, if alpha is a real number or plus infinity, then it'll be less than or equal to plus infinity. So notice that we're not going to be in a case where limsup and the limsup of this sequence or the limsup of that sequence is negative infinity, because our terms are non-negative, right? So 0 is always going to be a lower bound, so we can't have the limsups be negative infinity. And I'm looking at this, and this shouldn't be a sub n, this should be s sub n. So let me change that. So s sub n. Okay, so we want to show that alpha is less than or equal to L. And so let's just say case 1, L equals plus infinity. Then we're done. Then, so alpha is bigger than or equal to 0, or alpha is equal to plus infinity, since each term is bigger than or equal to 0. So L is bigger than or equal to alpha as desired. So that's the easy case. Let's move on to case 2. Which is that L is a real number. And notice that because we're taking the ratio of some non-negative terms, the limsup has to be bigger than or equal to 0. So let's just write that down. So since for each n and n, the absolute value of s sub n plus 1 over absolute value of s sub n is bigger than 0, we have that for each n, 0 is a lower bound, for the set the tail end of our sequence, right? So since 0 is a lower bound, the supremum has to be bigger than or equal to 0, because all the terms are bigger than or equal to 0. So our limsup is going to be bigger than or equal to 0. So let me look at this again. So I said since for every n our terms are positive, we have that for every n 0 is a lower bound. Okay, therefore sup of this set sup of this set is going to be bigger than or equal to 0. And that's true for every n. So limsup, right? So limsup is going to be bigger than or equal to 0. Okay. Now, remember our goal is to prove that alpha is less than or equal to L, and L is positive. So here's 0, and maybe L is somewhere. So say that's L. And here's how we're going to show that alpha, here's how we're going to show that alpha is bigger than or equal to L. What we're going to do is we're going to say if there's any number, say L1, that's bigger than L, then L1 is bigger than or equal to alpha. So there was a homework assignment that included the proof that if alpha is less than or equal to every number that's greater than or equal to beta, then alpha is less than or equal to beta. Okay, so we'll say fix L1 bigger than L. We will show that alpha is less than or equal to L1, right? This will imply alpha is less than or equal to L. Okay. So fix L1 bigger than L. So say here's L and here's L1. Now remember, L is equal to the limsup of your sequence. And the limsup of your sequence is the limit of a sequence that is decreasing. So your sups form a decreasing sequence, and your sups are going to decrease down here. So you'll have the sups of the tail end of the sequence, and they're getting closer and closer to L. So in particular, since L1 is bigger than L, that means that there has to be a sup that is less than L1. Yes. So since L is less than L1, there exists an n such that this set, or the sup of this set, the sup of this set is less than L1, bigger than or equal to L. Okay, so there exists an n, a big N, such that for all little n bigger than n, Sn plus 1, absolute value over the absolute value of Sn, is less than L1, right? So this is going to be less than or equal to the sup of this set. So if the sup is less than L1, then this has to be less than L1. So there exists an n such that for all of the terms past it, we have this inequality satisfied. Okay. Well, that just means there exists an n such that for all n bigger than n, we'll have the absolute value of Sn is going to be less than L1 times the absolute value of Sn. So the absolute value of Sn plus 1. Okay. But now notice that, or actually, that's true, but it's not helpful. Here's what I'm going to do. I'm going to write S sub n as S sub n over Sn minus 1, Sn minus 1 over Sn minus 2, Sn minus 2 over Sn minus 3, dot, 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 and then Sn plus 1 over Sn, and then times Sn. So don't forget we have this quantifier. We're saying for all indices past n, I can take it and write it as Sn and then times, see how the Sn minus 1 terms cancel out and the Sn minus 2, Sn minus 3. So all of the terms will cancel out. So everything's going to cancel out. I just need to go and add in absolute values here. And the reason why I'm writing Sn, the absolute value of Sn, as the product of these ratios is because this is going to allow me to estimate the absolute value of Sn. So the idea, here's a sketch of the idea. So the idea is that Sn plus 1 over Sn, absolute value of Sn plus 1 over Sn, the sup is bigger than L1, right? So that means these terms are bigger than L1, and that's true for all n bigger than n. So here's n, okay, n plus 1, n plus 2, dot, dot, dot. Say you're looking at your nth term. Now Sn plus 1, or Sn, how do I estimate the size of Sn? Well, if I look at this, then I'm thinking Sn plus 1, absolute value, is bigger than L1 times the absolute value of Sn, right? Okay, so that means that the absolute value of Sn plus 2 is going to be bigger than the absolute value of Sn plus 1 times L1. But the absolute value of Sn plus 1 is bigger than L1 times the absolute value of Sn, right? So that'll be bigger than the absolute value of Sn times L1 times L1. Okay, so you can repeat this argument to get an estimate for the absolute value of Sn based on how many terms it is past your big N. Okay, so if I have Sn plus k, yeah, absolute value, that's going to be Sn times L1 to the k, right? So that's fundamentally why we have this relationship between the ratios and the roots, right? Like, why is there a connection between the nth root and the ratio? Well, the answer is because if we're looking at this ratio and we know this ratio is bounded by a certain constant or is approaching a certain constant, then we can estimate the terms past, right, that index by comparing them to this one, right, looking at the ratio. Okay, so that's kind of the idea behind what we're doing. So we're saying there exists a big N such that for all of the terms past that, we're going to rewrite the absolute value of Sn like this. And now I can go back and use the hypothesis, not the hypothesis, but the premise that the ratio is going to be less than L1 to say this is going to be less than L1, this is going to be less than L1, this is going to be less than L1. Each of these terms is going to be less than L1, so I'll have that for all n bigger than n, the absolute value of Sn is going to be less than L1 to the little n minus big N times the absolute value of Sn. And so how do I know how many factors of L we have? Well, this is going to give me one factor. This is going to give me two factors. This is going to give me three factors, right? So one factor, two factors, three factors. So my last n, I need to just rewrite it as n minus something. And whatever the question mark is will tell me it's counting the number of factors of L1 that we have, right? So this is one. This is the second one, right? There's number 2. This is the third ratio. There's number 3. And I need to figure out how many ratios I have. I'm going to take big N and rewrite it as little n minus question mark. And whatever question mark is will tell me the number of ratios that I have. Well, I'm just going to write this as n minus little n minus n. So that's how I know that I have n minus big N factors of L1. And then, of course, don't forget that you have that absolute value of Sn at the end. Okay, so I'm now going to rewrite this. So I'm saying, so for all n bigger than n, I have the absolute value of Sn less than, let's see here, L1 to the n times the absolute value of S sub big N over L1 to the big N. Now remember, my goal is to make a relationship between alpha and L1. Alpha is looking at the limsup of the nth root of the absolute value of Sn. So I've got absolute value of Sn is less than this. I need to take the nth root. Luckily for me, this will be an increasing function. So I'm going to take the nth root of both sides of this inequality. Okay, and I'll say, so for all n bigger than n, the absolute value of Sn, the nth root of that is going to be less than L1 times, now I have the absolute value of Sn over L1 to the n, and I'll have the nth root of that. And now here, I say this is a constant. This term here is a constant raised to the nth, 1 over nth power, right? So as n goes to infinity, as little n goes to infinity, this is going to go to 1, right? Because you'll have a constant. It's like you have a constant to 1 over n. That's going to go to 0. So the whole thing is going to go to 1. Yeah. So this term right here tends to 1 as little n goes to infinity. Okay. So there's this a big N such that for all little n, I have this inequality. I'm now going to say that I can say that the limsup has to be less than or equal to L1 times 1, right? And so how do I jump from each term is less than this to the limsup is less than this? Well, so you have some index n, and all of the terms after that, so n plus 1, you know, all those terms after that satisfy this inequality. So when you look at the soup of the terms passed in have to be less than this, which is less than or equal to L1, right? So now if the soup is less than or equal to that, at some point the soups of the tails of your sequence will be less than 1. Remember, you're looking at the limsup will be the limit of that monotonically decreasing sequence of soups. So once one of the soups hits a number that's less than 1, the remaining soups have to be less than 1. So your limsup, the limit, has to be less than 1. Okay? So, or 1 times L1. So I've been saying. So limsup is going to be less than or equal to L1. So we're done. So to recap, we have shown that for each L1 bigger than L, alpha is less than or equal to L1. Thus, alpha is less than or equal to L. And that's what we wanted, right? That was our goal. We want to show the alpha is less than or equal to L. Okay. And again, step 2. So step 1 was to prove this one right here, which was easy. You say infs are always less than or equal to soups. So follow the definitions and you'll be able to prove that. And then proving this inequality here, we just did. And then proving the liminf versus the liminf for the ratio versus liminf for the roots is going to be similar to this one here. Okay. So as usual, let me know if you have any questions.